Hello everyone and welcome to this webinar on solar energy and perovskites. We are MAESTRO, a European training network funded by the European Union's Horizon 2020 Research and Innovation Programme under the Marie Skłodowska-Curie actions. MAESTRO stands for Making Perovskites Truly Exploitable, which is the aim of the project. Some of you may know that today is World Environment Day, and we hope that perovskites will be a part of building back better for the people and the planet. And thank you for being a game changer by taking part in this webinar today. We have 530 people signed up to this webinar, and as you can see on the right, this audience comes from a variety of backgrounds in terms of location, age, and background in perovskites. We also understand that not everyone can make this webinar today, so we will be making this recording available, the recording of this webinar available on our website, maestro-itn.eu. Our speakers today include myself, Anni Laihanen from the University of Bath in the UK, who is introducing this webinar, Nadia Klipfel from EPFL in Switzerland, Thijs Mulders from the University of Bath in the UK, Christina Kamaraki from Oxford PV in the UK, Vivek Babu from Saule Technologies in Poland, and Luigi Angelo Castriota from Tor Vergata University of Rome in Italy. This webinar is organized into 5 parts. Nadia will start the presentation off with some global warming facts. Thijs will then discuss the benefits of renewable energy, after which Christina will introduce the basics of solar cells. Vivek will present the magic of perovskites, and Luigi will conclude the presentation by introducing our project MAESTRO in more detail. We would like to invite you to write any questions in the chat, as you are your microphones have been muted, and we hope that you enjoy the webinar. I will now pass over to Nadia.
Racism, Corona, Trump. So many headlines in the news nowadays. But there remain many other topics that one should draw attention to. Climate change is one of them. Trump, among others, thinks that climate change is a hoax. But luckily, there are many scientists around the world that think differently. Climate change is real, as you can see here in this temperature anomaly chart recorded by different research organizations around the world since 1880. Nowadays, we reached a temperature change of 1 degree. But the impact of this climate change upon Earth you can see even more severely when you're looking at this video here from NASA. The dark blue regions indicate the temperatures below average, and the dark red regions the temperatures above. As you can see, with time passing by, more and more surface area of the Earth is becoming dark red, which indicates temperatures above average and too high. But the temperature increase on Earth is mainly caused by mankind. With introducing greenhouse gases into our atmosphere. Greenhouse gases are gases which trap the thermal radiation or the heat on Earth like a blanket. And they're mainly caused by burning of fossil fuels or fires that humans induce to our Earth. When you look at this chart here, there's the CO2 concentration recorded in parts per million since 800 million years ago. Normally, the level always stayed around under 260 ppm, but then suddenly in 1950 there was a strong increase in CO2 emissions to the highest historical CO2 level recorded then. But as you can see, now we even reached 400 ppm in the current state. So we surpassed this a long time ago. But luckily, the Earth was designed to be in balance. So not all the CO2 emissions that we produce per year which are 36 billion tons, are staying in the atmosphere. Natural things such as plants, which use the CO2 for photosynthesis, or the soil, which incorporates the carbon and biomass from degrading plants, are absorbing more than half of our emissions. The data, like I have just shown you before, is recorded by satellites. The most famous satellite which records the temperature anomalies around the Earth is the ECWA satellite, which was launched 2002. It is so special because it carries 6 different instruments that can monitor the global water and energy cycle, the climate variation, and the response of the climate system to increase greenhouse gases. There is also another satellite which can measure the CO2 in our atmosphere. This satellite is the OCO2 satellite, which orbits around the Earth and scans the whole atmosphere within 16 days for the CO2 concentration. It has a special system, which is a high-resolution spectrometer, which can measure with near-infrared absorption the sunlight which is reflected by CO2 or oxygen. So from the fingerprint spectra, we can really identify which molecule is in the atmosphere and how is the concentration. So the satellite is mainly used to identify the CO2 sources, to identify the natural things and predict can they absorb maybe more CO2 during this year, and to verify the analysis method towards optimization, because we want to be sure that in our future all the calculations we do for our concentration of CO2 are correct, so we can really think about more solutions of this problem. But of course, everything is connected. We have the increasing greenhouse gases due to the increasing CO2 levels, and therefore, of course, we also have the shrinking ice sheet. When you look here, in 1979, the ice was quite big, still covered on Earth. It already shows a strong decrease in 2019. But I think looking at the numbers makes it even more severe. We have in the Antarctica a mass variation of 147 gigatons per year. But even in Greenland, it's much higher. It's 280 gigatons per year. This is incredible, I would say. And when you look at the graph, which was here on the y-axis, million square kilometer of ice sheet lost over the years, we see a steadily decrease. But this cannot only be seen from pictures from the space. I brought you here these 2 pictures from an actual hike from last week. But let's start here. The Aletsch Glacier is one of the largest glaciers in Europe, located here in Valais in Switzerland. In 1865, this picture was taken where you can see that the whole valley is covered with ice. But now, in 2010, everything has melted away. But with the decrease of ice, also other problems arose. The pressure on the ice of the mountain suddenly vanished. So since 2016, a visible crack, which I indicate here, was suddenly appearing in a mountain which has an altitude of 2,500 meters. It is predicted that soon this mountain will crash into the valley where the glacier ice formed. So all these environmental changes that I just talked about are direct results of climate change. We have more of them. For example, in Australia, we had severe burning of the forest. Also in California, it was recorded during the last year. And even Norway recorded the warmest winter in January with 19 degrees. So what can we do to flatten the curve of climate change? During the confinement period of COVID-19, government upon the whole world implemented policies, drastic policies upon us in our society. So how did this change maybe positively the CO2 concentration in our atmosphere? When we look at this chart, we have here again the concentration in ppm and here the years. So we see a steadily increase, and in red we see the prediction for these few months of confinement, and then the actual curve is the one in blue. So it was calculated that the corona confinement decreased the CO2 global emissions for 8%. But is it enough? That's the question. One could only see that during the confinement period, the air pollution in China decreased rapidly. This is here from the images. Actually, a nice result. But some scientists look deeper into this problem and analyzed why did the CO2 emission decrease. So here is the change in daily fossil fuel CO2 emissions, and they found that power, industry, and surface transport had the most impact on decreasing of the CO2 levels. A little bit less the planes that started flying and the public transport. Interestingly, of course, we had a small increase in CO2 emissions from the residential housing as everybody was staying at home. Strong measures like confinement, stopping of industry can of course not be the solution towards a most sustainable world. There's different steps that can be implemented into society which can help flattening the curve. One of the steps is to raise more awareness in the society about all the problems that we face with climate change. Therefore, the UN has implemented climate advocates by asking famous actors or football players or models to speak publicly about climate change, to just increase the overall awareness of our problems. But this is of course not enough. Raising awareness is the first step, but there must be more measures. So industries are the main cause when it comes to CO2 emissions. Implementing sustainability into their strategy is therefore crucial or necessary to increase their impact and stopping climate change and flatten the curve. 101 companies announced to be CO2 neutral by 2030 and then even CO2 negative by 2050. The Earth was designed to be in balance. Let's continue our new starting approaches to flatten the curve of climate change. With this last cartoon, I would like to give over to my colleague Thijs, who will continue speaking about the chances and challenges of renewable energies.
Thank you very much, Nadia. So as said, we'll continue now with a more quantitative analysis of renewable energy in the current mix. But before we start, I would like to sort of introduce the definition, so to say, to have a common ground for what we talk about. So renewable energy can in a way be described as energy coming from renewable sources that are naturally replenished on a human timescale in a way that they can be used sustainably by many generations, meaning that if we use generation today, it should not eat into the supplies of future generations, so our children, grandchildren, and beyond. And this nice cartoon shows a few different examples, of course, of renewable energy. If you're interested at all in this stuff, I could not recommend reading this book more. It's called Sustainable Energy Without the Hot Air by late David McKay. It's available for free if you go to this website, available in a few languages as well. And it's very accessible, meaning that it's written in a very easy to read language and does some back of the envelope calculations with like some profound sort of physical insights. And also for the more technical reader, there's some technical chapters at the end. But it creates a nice sort of setting between sources of renewable energy and our consumption patterns and tries to find the balance, because in the end, that's what sustainability is about, if we can produce as much as we use or the other way around. If there's another thing I want you to take home from this part of the talk at least, and to set the next few slides into perspective, is this 20% rule, meaning that in 2020, it holds that about 20% of energy consumption worldwide comes from electricity. And people sometimes wrongly interchange these two, as seen in this tweet, where it originally said Costa Rica is now running on 100% renewable electricity, which is wrongly retweeted as Costa Rica is now running on 100% renewable energy. But it's only about 20%. The other 80% typically goes to transport, so vehicles, etc. And this is a graph showing the average share of electricity in the energy mix for Europe, for different countries. And you see that on average, the European Union has about 20% of its energy coming from electricity. And then the other 20% rule is that 20% of this electricity is renewable on average. And here you see a graph going from the 1970s to almost today. And it's quite a steady line going from showing that other renewables, apart from hydroelectric, which is the biggest one being mainly dams, constitute about 20% of our sort of supply for the electricity sector. The rest coming from mainly fossil fuels, being coal, oil, and natural gas. Then going into what the potential of different sources of renewable energy is, because of course we have plenty to choose from. This graph nicely shows graphically what the extent of different technologies is compared to our average consumption every year worldwide. So this is 16 terawatt years, which of course is a lot bigger than what you typically see in your energy bill. But we can compare it to different technologies, being, for example, geothermal, hydro, and here you see that wind is relatively big as well. And we can also compare it to the reserves that we have for non-renewable sources, mainly fossil, being gas, oil, and coal. And here is also some nuclear. But what strikes the most in this picture is the massive size of this yellow sphere that represents the sun. So the extent of our solar potential in principle is massive. And a nice anecdote on this, or a nice way to visualize this, is if we were to be able to theoretically get all the energy that the sun brings to our Earth, so the irradiation, say just outside the atmosphere, we would only need to harvest this for about an hour every year to be able to fully supply our energy needs for that entire year. So as I said, the potential of solar energy is enormous, but we're not quite close in terms of our current production. So this shows that energy consumption and coming from different sources from the 1800s to today. And what you can see is that it's we started using fossil fuels in the early 1800s, which coincided with the Industrial Revolution and our awareness that we could power our steam engines with coal, being the first fossil fuel that we massively used. Apart from where we started off with traditional biofuels being mainly wood to heat and cook. And since we've rapidly increased our consumption needs, and they've been powered mainly by fossil fuels, being coal, crude oil, and natural gas. And only in the very top few percent do we see some renewables coming into the mix. And to zoom in a little bit, so we use more than 140,000 terawatt hours today, and about 6,000 of those are actually renewable if we omit the traditional biofuels. So those are mainly hydropower still, being dams, as I said, and we have a small section of solar and wind. So to look at the numbers a bit more, this brings into practice the 20% rule. Because if we take 20% of energy being electricity and 20% of electricity being renewable and emitting all other renewable sources being transport, say, then we see that about 20%, if we multiply those, we get about 4% of our energy total being renewable, which corresponds indeed to this percentage of 6 out of 140. So we really see that we have a lot of catching up to do, and we have limited time to do that, so we have no time to waste. Specifically, if we look at the reserves that we have in terms of fossil fuels, we can look at this in terms of how many years of different sources we have left. And we see that for oil and natural gas, we have about 50 years left on an economic scale, if we look at how, which sort of reserves we can tap into with limited cost. For coal, this is about twice as big. But that doesn't mean that we can use all of these sources, because that would bring us into big trouble. So this is shown in this right graph, where we see the total amount of reserves that we have left in terms of the emissions that would correspond to them if we were to use them, and what would correspond to a budget that would keep us probably, not even surely, below a rise of 2 degrees, which is the limit set by our conferences and IPCC measures. So yeah, we really have to catch up, and we have to do it soon. But there is a silver lining, and that is that renewable technologies have become increasingly cheap over the last few decades. And this is shown in this graph, which nicely shows the average cost of solar PV modules compared to the cumulative capacity, so how many of them we have installed. And we see this rapid decline over many decades to levels below $1 per watt today. And this is mainly due to 2 reasons. One being simply an economy of scale. So we've invested in this technology, and because some of our investments have been one-off investments, we can divide them over a bigger installed capacity, and we can thus average our investments over more panels, making them cheaper. Plus, our supply chain has become more efficient as well. But also, and we'll stress this later on in the next part of this talk, we've seen a lot of technological development in terms of how we make these PV modules. And that's what research has really been guiding us towards, and what we're still working on. So to put this into perspective in terms of fossil fuel prices, this is a new graph which only came out a few days ago by Irina, and it shows us the levelized cost of electricity for different technologies. And this levelized cost of electricity is basically a measure to compare like for like and different technologies by just dividing their costs, so investments, maintenance, etc., by how much energy they actually produce. And although they vary large per country, this is an average measure taken over mainly the US, China, and then taking the rest of the world's averages. But we see it specifically for PV, which are these yellow bars. We now really get to levels below what is typically assumed to be fossil fuel prices. So since like in the last decade, we've really made another step to bring the prices below fossil fuels, and we're really like starting now to become really competitive with fossil fuels, which should mean that in the future, in the near future, we should see a lot more PV popping up. Another cost aspect that I want to sort of mention here is the environmental cost, or maybe the cost to humans, and this shows so the level of danger that corresponds to different technologies compared to the average greenhouse gas emissions that go with these technologies. And you see on the top right that coal is both very dangerous and emits a lot of greenhouse gases. And of course, there's a correlation between those two because of air pollution. And in the very, very bottom left, we see all these renewable sources being hydro, solar, and wind. And specifically solar is about 1,000 times less dangerous if you look at the number of deaths per terawatt hour, and emits less than 1% of greenhouse gas emissions compared to coal. So they're much, much cleaner, and also compared to oil and natural gas, of course. And interestingly, also nuclear energy is shown here in the bottom left. So contrary to maybe common opinion or the media, it's actually relatively safe if you look at the numbers behind nuclear energy. So now that we have a feeling for the scope and what's currently out there, we know that we have to move forward. So what are different ideas out there? So I'm going to highlight the European Union plans because that's sort of part of our, I mean, we work in Europe. And specifically, I want to highlight a few of their directives. One being introduced in 2009, which announced that they want to be 20%, have a 20% mix of renewables in the energy mix by 2020. A few years ago, this was taken to the next level by like demanding 32% of renewable energy in the power mix by 2030. And even more ambitiously, this year it's been proposed, hasn't been accepted yet as far as I'm aware, it's been the European climate law, in which they like stated they want to be the first carbon neutral continent by 2050. So yeah, that would be very, very nice to see. And we'll definitely try to take our part, all of us. So because of course we're now in 2020, we can have a look at how close we have gotten so far. So I should mention that including, so this 20% renewable energy in total, but additionally, they also want to have 10% of the, say, 80% of transport that I mentioned to be renewable as well, to not hamper that development. So in 2020, I mean, these are graphs 2018, we see that even though the variations per country are large, and me being Dutch makes it a bit awkward, on average, we get relatively close to this level that we set, being 20% renewable energy in the mix. And the same holds in principle for the level of energy in transport, that variations in countries are big. Although we don't get as close as the full energy mix, we're now really trying to improve our share of electricity powered, or maybe even hydrogen powered in the future cars in Europe. Before we move on to the more technical bits, we want to sort of take a small step back and summarize what we've seen now, and maybe specifically look at what you can do. And because it's World Environment Day, I want to also highlight the fact that we have a concept called the World Overshoot Day, and that has been announced today. So to introduce you to this concept, World Overshoot Day basically is a measure of how much we could, in principle, produce in a year in terms of our food, transport, etc., building. And then they look at what point in the year we've actually used up all of that supply. Meaning that from that day onwards, we eat into the supplies of our future generations. And it's been announced today that this day in 2020 falls on August 22nd, which is a bit further away than has been the case in previous years, due to, of course, the coronavirus crisis that we've all been facing. But still, it means that we have, there's like a long way to go to bring this all the way back to the 31st of December and even beyond. So interestingly, also this is shown per country. So if you want to have a look later, there's you can go to World Overshoot Day or overshootday.org, and you see that for different countries, these values, of course, massively differ. And you see that for some European countries, they even go into April, March, or even February. Meaning that if it's in the end of February, you probably need about 6 Earths on average per citizen to be able to meet the demands, which of course is a lot, and we should really try to tackle this. So more specifically on a smaller scale, what you can do, one nice website to have a look at is this one, which is the footprint calculator, and it shows specifically, if you take the test, I can show you quickly what sort of impacts on a sort of personal level are. So one being food. Specifically, I really like veggies. I'm a vegetarian. I still eat dairy and eggs sometimes, so I'll set this scale to here. I try to eat some local food, but obviously, I guess still some of my supermarket stuff comes from further away, so I have no control of that. Maybe 35. I live in a duplex house, which is made from brick. I share it with 3 others. So it sounds about right. It's not that tiny, but I guess medium. Huge would be massive, not the rich yet. I have electricity, otherwise I couldn't host this session. Being in the UK, energy efficiency of houses is not massive, so let's put it a bit to the left. Electricity share, renewable share of electricity, I think is relatively high in the UK, so let's put it at 40. I don't think we use that much waste. I don't have a scooter at all. I don't typically drive. I sometimes drive with my husband to uni. That's only a couple of days a week, so let's bring this down a bit. Yeah, that sounds about right. Doesn't really matter. I said I always, if I go by car, I carpool. I guess this is about the number of trips I would take if I were to. I don't really use public transport that much, but I guess if I go home, this might be reasonable. And here I have taken my total number of flights, I guess, in my life and divided by my age. So let's see what this amounts to. 2.1 Earths. So it's more than I thought previously. That's yeah. I mean, even I try to be progressive, but I guess painful. There's still loads to do. So don't look at this. This was maybe a different setting. But in principle, if you like, I would urge you to do this yourself, because it's actually sort of a painful acknowledgement of how much we use on average. And some things that you could try to do yourself are some of these, which I want to highlight these 3, maybe, for example, being all transport related. So transport is really a big source of our energy consumption. I'm not saying, so here is, for example, a vegan diet, which of course will make a big change as well. But you have to be sure that you know the numbers behind the things that you do in terms of making a change. Because, for example, being vegan for a year would amount to the same number of energy if you remove one less long-haul flight. So yeah, be sure to look at the numbers if you want to change something. So without further ado, I think I would like to give the floor to Christina, who will tell you more about the actual technological developments we've seen in solar cells. We cannot hear you, Christina.
Okay, I'm sorry for that. Are you able to see my screen?
No.
We were just now, and now, yeah.
Now? Okay, let's try once again. This one? Does it work?
Yes.
Yes. Yes.
Cool. I'm so sorry for the
Go on.
delay. So, hi everyone. Thank you, Thijs, for the nice introduction on the potential of solar energy. So now we will jump into a bit more physics and see how solar cells work and what are the representative solar cell technologies that exist by far. So let's see how everything started. So at 1839, Edmond Becquerel was the first one that claimed that by shining light on an electrode that was submerged in a conductive solution, he was able to measure some current. Some years later, Wilby Smith discovers the photoconductivity of selenium, and 10 years later, at 1883, Charles Fritz is the first one inventing the first solar cell made from selenium with efficiency only 1%. Unfortunately, we have to mention here that the explanation of the photoelectric effect by Albert Einstein was a milestone for the evolution of solar cell technology and was actually the reason why he received the Nobel Prize in 1921. So it took the scientific community 50 years to finally demonstrate the first modern solar cell made from silicon with efficiency at 6%, which was invented by 3 engineers at Bell Laboratories. The next 40 years were a journey of advancements in processing and manufacturing procedures, and also better understanding the science behind the solar cells. And we ended up by having this really fancy and complex silicon solar cell structure with efficiency up to 25%. So from 2000 until now, scientists were really eager on improving the stability and the efficiency of these solar cells, but also they were really curious to explore new materials and substitute silicon. So by now, we have 3 generations of photovoltaic technologies that I'm going to explain you in a while. So let's see now how a solar cell works. The working principle of a photoelectric effect is based, of a solar cell is based on the photoelectric effect. The photoelectric effect is a phenomenon that occurs when we shine light on a metal surface that causes the ejection of the electrons. So according to classical physics, light is a propagating electromagnetic wave. However, scientists were unable to explain photoelectric effect using classical physics. They were expecting that regardless of the frequency of the light, at some point, even after prolonged illumination, the electrons will have gathered the appropriate amount of energy and they will be able to escape of the material. However, this was not the case. It seemed that there was a frequency threshold. So for example, when the frequency of the incident light was low, let's say in the red region of the visible spectrum, then no electrons were ejected, even though they were illuminating the sample for a long time. When the frequency of the incident light was a little bit higher, let's say in the green area, then some electrons were ejected. And then when it was even higher, the same amount of electrons were ejected with higher kinetic energy. So Einstein came and proposed that actually light is not a wave propagating through space, but rather a collection of discrete wave packets which are called photons. A photon is a particle of electromagnetic radiation that has 0 mass and carries a quantum of energy, which is proportional to frequency, as we can see here from this equation. So only photons that have a frequency or energy higher than this threshold will be absorbed and thus lead to the excitation of electrons. So let's see now what defines this frequency threshold. So as you might probably all know, we can distinguish materials in 3 main categories regarding their conductivity. Here is an energetic diagram which describes the conductivity of materials. So as you can see, it consists of 2 bands. We have the lower band, which is called valence band, and it's actually where the electrons are located, strongly bonded with the atoms. And then we have the conduction band. This is usually empty, and it's the region where the electrons can freely move. As you can notice, there is a certain gap between the valence band and the conduction band. This distance is named energy band gap, and it's what defines this frequency threshold. So for insulators, we need a large amount of energy in order to excite electrons to the conduction band. whereas in semiconductors, the value of the energy bandgap lies in the visible spectrum. In case of conductors, we cannot refer in energy bandgap because usually the conduction and the valence band are overlapped. So if we want to excite an electron from the valence band to the conduction band in a semiconductor, it just needs to absorb a photon with the right amount of energy, which is higher than the bandgap. So if it absorbs the photon, it jumps to the conduction band, leaving behind a gap. This gap is considered as a positively charged carrier, which is named hole. So it's the opposite of an electron. So as you can see also here, with the example of potassium that has a bandgap of 2 electron volts, only photons with higher energy than the bandgap are absorbed, and thus leading to the extraction of electrons. So bandgap is what defines the absorption of light or the absorption of photons. So we have two different types of bandgap, the direct bandgap and the indirect bandgap. In direct bandgap, the photon absorption is just a single process. So the photon is absorbed and then the electron jumps to the conduction band. In case of indirect bandgap, another process is involved. So apart from the photon absorption, the so-called phonon absorption or a lattice vibration needs to take place in order to excite the electron to the conduction band. So as you can imagine, because two processes are involved, the photon absorption is quite less probable than in case of direct bandgap. So keep that in mind because I'm gonna come back to it. So once we know now how we can absorb light, let's see how we can make a solar cell. First, we need to find the absorber. Here is the solar spectrum, which describes the amount of energy that arrives at Earth's surface. So as you can see, the maximum of the energy lies on the visible region of the spectrum. So definitely we want to absorb this amount of light and of course even lower energies. So we need to find an absorber. Usually when we investigate new materials, first we do some theoretical calculations in order to determine in principle the bandgap and structural properties. And then we go down to the lab and try to validate these calculations experimentally. So let's say that we have found a semiconductor, let's say silicon, that has a bandgap around 1.1 V. So it starts absorbing from here and onwards. And we need to make a solar cell. Do we need anything else apart from two metal contacts to extract the carriers? So the answer is yes, we need selective layers. So an electron, even if it is excited to the conduction band, usually it prefers to return back to the valence band where the energy states have lower energy. So in order to avoid this relaxation, we need to pull the electron to the contacts, and thus we need a driving force. This driving force is provided by the selective layers. So these selective layers need to fulfill some specific energy requirements that I'm not going to get into more detail now, in order to extract effectively the carriers. And also they need to be compatible with the absorber. So for example, not chemically react with the absorber or induce any degradation that will deteriorate the solar cell performance. So here is an illustration of a common solar cell configuration. So as you can see, we have an absorber, which is sandwiched between the selective or the so-called transporting layers and the contacts. And in this way, we can power a light bulb, for example. So let's think how much energy actually we can absorb and what will be the efficiency of our solar cell. The efficiency is defined as the ratio of the power output, which is actually a product of voltage and current, over the power input. Unfortunately, we cannot have efficiencies 100% or 90% because there are some inevitable losses. First of all, the major loss is the so-called thermalization loss. So this loss stems from the high energy photons. As we mentioned before, when a photon of high energy is absorbed, then the electron has higher kinetic energy, which is excess and we cannot exploit it. So it's lost as heat. Then we have some losses due to photons that have not been absorbed because they have energy lower than the energy bandgap. And some losses around 15%, which are extraction losses and come from resistances to the selective layers or the contacts. So the available percentage is 33% and it's called Shockley-Keyser limit. So, of course, a solar cell, in order to be commercialized, it needs to be efficient, low cost, and stable. By far, there are 3 generations of solar cells. We have crystalline silicon solar cells, thin film technologies, and emerging photovoltaic technologies. Let's go to the first generation, which is the crystalline silicon solar cell technology. As you can see here, this is a picture that depicts crystalline silicon solar cell modules. So a module is a configuration that consists of single solar cells that are interconnected. Crystalline silicon solar cells are made of silicon wafers, which are really thin pieces of silicon. The fabrication of silicon wafers is a high temperature procedure. So first we melt the silicon, and then we create elongated crystalline bars, and then we cut them in really thin pieces. We have 2 different types of crystalline silicon wafers. The monocrystalline silicon, which come from a single crystal of silicon, and that justifies its shape. So as you can see, it's polygonal, and that's why we have these gaps in these monocrystalline modules. Or we have the polycrystalline wafers, which are actually rectangular. They consist of fragments of silicon, and as you can see, all the edges of a solar cell are in contact with the neighboring ones. Crystalline silicon solar cell technology is a major technology because it has been progressing the last 70 years. The efficiencies are really high, up to 26%, and we have the advantage of the low gap of crystalline silicon, which is 1.1 eV, so we can absorb a wide spectral range. Unfortunately, the band gap of silicon is indirect. So as we mentioned before, the absorption of a photon is less probable, and that's why we do thick silicon layers. So the thickness is around 200 micrometers, and to give you an idea, imagine that our hair has a diameter of 2 micrometers. Also, the fabrication of crystalline silicon solar cells is a lengthy and complex procedure that demands high temperature, which quite increases the cost. And also, silicon is quite intolerant to defects, so we need high purity conditions. However, it's not only silicon. In this graph, you can see an efficiency chart over time with all the existing solar cell technologies. So the hero efficiency of a single solar cell is for gallium arsenide. However, this solar cell cannot be used in domestic applications because they contain arsenic, which is quite toxic, and also their fabrication is really high cost. So that's why they usually have been used in space applications. So let's explore a little bit the other solar cell technologies. Moving on to the second generation of solar cells, we have the thin film technologies. So the main feature of this family of solar cell is that we have absorbers with direct bandgap, and thus we can have thinner absorber layers up to 10 micrometers. So imagine 1 order of magnitude lower than the crystalline silicon. So in this family, we have first amorphous silicon, which has a bandgap of 1.7 V, but unfortunately, its efficiency is quite low. It's around 14%. So this is quite limiting for large area applications. However, amorphous silicon solar cells have been used in consumer electronics, like the old school calculators that we used to have back in the 90s, before they have been substituted by our smartphones. Then we have cadmium telluride. Cadmium telluride has a direct bandgap of 1.5 V and efficiency is up to 22%. Even though their manufacturing cost, the use of cadmium, which is toxic, and the scarcity of tellurium are the main drawbacks. And then we have copper, indium, gallium denied, or CIGS solar cells. So these type of solar cells have the unique property to tune the bandgap because we can play around the composition and the ratios between these 4 materials. And also they can be fabricated in flexible substrates using electrodeposition method. However, the scarcity of gallium and indium and the use of cadmium sulfide as a selective layer is again prohibiting. Also, these nice efficiencies of up to 23% cannot be replicated in large area modules, which is again a drawback. And now we have the emerging photovoltaic technologies. So this family of solar cells can be fabricated via solution-based methods, which is a great advantage because we can use high throughput techniques like roll-to-roll techniques, which are similar to printing newspapers. So you can imagine the high throughput. And also we can play around with different polymers and organic materials and tune the band up and have a wide range of absorbers. So in this category, we have organic photovoltaics, which have an efficiency of 18%. They are not toxic and they can be fabricated on flexible substrates. However, they lack of stability and they have short lifetime. Then we have the dye-sensitized solar cells. These type of solar cells are quite, let's say, strange because they are photochemical solar cells. As you can see here, we don't have a single layer of absorber, but we have small molecule dye molecules. So these molecules are actually absorbing the light and generate the carriers. However, the generation of the carriers leads to the oxidation of the dye. So a liquid electrolyte is needed in order to regenerate the dye and bring it back to its original state. The presence of the liquid electrolyte is a drawback because it induces a long-term instability in the solar cell. And also the fact that we need to regenerate the dye costs us some energy. So that's why we have lower efficiencies up to 12%. And then we have the next big thing in solar technology, which are perovskite solar cells. They have been characterized as the fastest evolved solar cell technology since the efficiency jumped from 3.9% to 25.2% only in 10 years. Imagine that for silicon, it needed 40 years to reach 25%. So again, we can tune the band gap, have flexible substrates, and use solution-based methods. But again, we have some stability issues and also the use of lead, which is considered as toxic, is quite a controversial topic among the scientific and industrial community. Last but not least, we can play around the different types of solar cells and combine them. So we can have the so-called tandem solar cells. The main idea of tandem solar cells is to exceed this Shockley-Keyser limit and surpass 33%. So in this case, we usually use a wide gap material and a low gap material. Usually on top, we have the wide gap material, which absorbs the high energy photons, let's say from green and onwards. And then the rest of the light passes through the wide gap cell and meets the low gap cell. And then these low energy photons are absorbed. In this way, we can have even higher efficiencies. And as you can see, already people have been trying either combining solar cells of the same technology like perovskite or OPV, or combine different technologies like perovskite on silicon or dye-sensitized solar cell on CIGS. So as you can imagine, the solar cell field is quite huge, either in academic or an industrial point of view. And there has been made a lot of progress, especially in alternative solar cell configurations. So now I will leave the floor to my colleague Vivek, who is going to introduce you to the magic of solar cell, of perovskites, and I hope he will convince you.
Thank you so much, Christina, for explaining the history and different generations of solar cells and the basic principles of photovoltaics. So here I would like to talk in general about perovskites, the properties, what it's making outstanding from other PV technologies, as well as the market potential of it, and also different companies working on it. Also, I will address the stability issues and different methods, how we can overcome it. So, as you can see in this picture, so perovskite is actually a class of material which is like making the earth of like 38% of its volume. And it is the class of minerals which having the crystal structure ABX3, as you can see here, where A is like this green sphere having a positive charge, which is like a mono or divalent cation. And this green sphere is surrounded by 8 octahedral cages. And these 8 octahedral cages are made up of this B, this purple sphere, which is a di or tetravalent cation. It's also a positively charged cation, and it is shared by negatively charged mono or divalent anion. And you can see in this figure where like the perovskite crystal structure. And based on what we put on the X side, if it's like a oxygen atom, we can call it as like in the oxide-based perovskite. And this is one of the very famous one or popular one, which is a calcium titanate in this picture. And if we work on different with halides on this X side, you can have the semiconducting property, and which enables us to the realm of photovoltaic technologies. And here I would like to more talk on photovoltaic application. So as I showed you already here, like this octahedral cages, what we can do with this, like we can tiltage, distort the structure and form other structures like the tetragonal, orthorhombic, rhombohedral structures. And what is the advantage, as well as it can change its electronic, mechanical, or like magnetic properties, and it opens up to us wide spectrum of different other properties like ferroelectricity, pyroelectricity, superconductivity. But here I like to talk more on the photovoltaic applications of it. So now I like to talk about like bit on history of perovskite. In the year 1839, Gustav Ross, a German scientist, was hiking through the Ural Mountains in Russia, and he discovered this amazing crystal mineral like calcium titanate, and he named it after the Russian mineralogist Lev Perovsky, as you can see in this picture. And over the years, perovskite was used in different applications like condensers, electromagnetic transducers, or piezoelectric resonators. And in the future, 1994, David Mitzi in his lab in IBM research, he developed the perovskite for the first application of optoelectronic devices. And this is like super amazing work where he basically explored on optoelectronic application. And before going further, I like to also mention the great invention by Professor Michael Greitzel on dye-sensitized solar cells, which works on the basic principle of photoelectrochemical effect. Christina already have explained on it. And in the year 2009, Professor Miyasaka in Japan, with his colleagues, he basically changed the dye in the dye-sensitized solar cell with perovskite sensitizers and got an efficiency of 3.8% efficiency. Later in the year 2011, Professor Namgyu Park, he developed those layers and got a higher efficiency of 6.5. And in the year 2012, Professor Kanasedis, he made solid-state dye-sensitized perovskite with 10% efficiency. And also the same year, Professor Henry Smith in the University of Oxford, he made meso superstructure perovskites. So now I like to talk some interesting properties of perovskite, which is making it outstanding from other technologies. The first one is like the absorption coefficient. So Christina already mentioned about the direct and indirect band gap in the case of perovskite technology as well as silicon. As you can see in this graph, the perovskite, the one over here, which is really higher compared to the crystalline silicon. And what absorption coefficient is, it determines how far into a material of a particular wavelength can get like before absorbed. So if you see at a particular wavelength, the perovskite crystal have a higher absorption coefficient compared to the first generation crystalline silicons. So another wonderful property of perovskite is also the ability to band gap, ability to tune its band gap. So this picture I showed in the first slide. So what we can do, like change these anions and cations and put some other or play around with this different atoms, and you can see which can form in different colors as well as absorbs in different spectrum of electromagnetic spectrum from 400 nanometer to 1100, which is super amazing because we can utilize this in different applications like in tandem, for example. And another interesting property is the multidimensionality of perovskite. So this is the one, you see the three-dimensional perovskite. We can basically slice it down, for example, with the large organic cations and act like a spacers. And why we need to do this is that it also seems the scientists found a higher stability in the perovskite material, as well as lately it also seems having a higher quantum yield in the case of which can be used in light emitting applications as well. And also it's also mentioned to high defect tolerance due to the anti-bonding nature of perovskite. So these are all the amazing properties of perovskite which makes it different from other technologies. So now I like to talk about, so now we already came to know about the perovskite, its properties. So now how we can make a device out of it. So here in this image, you can see the perovskite over here, and we shine a light or a photon or sunlight as well. So basically we excite the electron, and through one terminal, the electrons jumps to one side. At the same time, the holes will pop up and goes to the other terminal. We just connect a load and we generate electricity. This is like a very simple basic principle of photovoltaics. And here I showed especially in the perovskite. And these are the two device common architecture which is used. One is NIP and one is PIN. What difference it is? Like, it's very simple. Like, onto the substrate you have a electron transport material, and you basically take out the electrons through the substrate layer. You basically, or the electrode close to the substrate, you have NIP. At the same time, when you extract the holes through the electrode close to the substrate, you have a PIN planar architecture. And another one, if we basically change the transport material to a mesoscopic structure, which is like a porous material, we can also have NIP mesoscopic, PIN mesoscopic. So these are like the basic device architectures used by scientists for fabricating devices with the help of perovskite material. But it's important to note that the electrode needs to be transparent and conductive. Why? It needs to be transparent so that the photons can reach the perovskite layer. And also the transport material should be having low optical losses so that you can harvest a lot of energy out from it. And also important to note about the compatibility with the solvents. This I will talk more in the process, but actually, like when you have a layer on top of perovskite, it's also important to select the solvents which are compatible when we put on top of the perovskite layer. So now I will talk also one amazing property of perovskite is the solution possibility, which is wonderful when you compare how we make the silicon wafers. But here it's so amazing. Like you can see, you basically have two salts. You mix it together in a solvent. For example, the one is a metal halide, the other one like an organic halide. You mix it with a solvent. You have this yellow, like it looks like an orange juice. Like you can say. So this solution, what we can do is basically just put it onto a substrate. You spin it, you remove the solvent, and you have this nice brown crystal perovskite you can see in this image, which is basically can act as a photovoltaic application. And later, we can also take the advantage of other processing techniques. For example, like in inkjet printing, you basically have the solution, you put it onto a printhead, like the one you have it in your office or home. You print it, you can have your own shapes or your pattern, which makes it, which opens like to have a ability for freeform shape. And I also like to mention about this perovskite crystals can be crystallized in very low temperature. So what advantage is it? Like we can coat it onto flexible substrates, mostly like plastic material, which can be degraded like in higher temperatures. So without destroying the substrates, we can crystallize this perovskite in low temperature, and this can be utilized for in roll-to-roll manufacturing, as you can see here, where you have an unwinding roller, you have a rewinding roller, and you basically just crystallize like Christina House when she mentioned about this newspaper printing, for example. And this really gives out high throughput and also yield in the production process. Now I like to mention also about the efficiency of perovskite. So if you see this small spin-coated cells, which is like a small area, over the past like 8 years, it really like shoot up, and you can see like it went to 25.2% efficiency, which is really amazing when you compare to other technologies where, for example, in silicon, it took around 40 years to reach the highest efficiencies. And also there is another chart from NREL. They also give the efficiencies of larger modules, for example, like in the larger areas, like in this picture you can see. And also it has an amazing efficiency of around 60%, which is quite impressive when you compare taking from the small cells to a really large areas. So this also makes like makes amazing when compared to other techniques. Yeah, when you think about commercializing the solar cell devices into our like a product into the market, we need to also keep it in mind the lifetime of these devices, because it's very important. It is like no one really wants some technologies like which works for a few days or few months. So it needs to be really important. And unfortunately, like perovskite can get degraded in the presence of moisture or oxygen, like you can see. Over the hours, you see this perovskite, which was having photovoltaic property, get degraded and forms this yellow phase, which is non-photovoltaic. So what actually we can do with this is to have a hydrophobic, we can actually coat a hydrophobic surface on it, or we can have a proper encapsulation, which can prevent this water or moisture to enter inside. Here you can see an image of a perovskite module inside a box of water. So you can see it can get out from this external degradation factors. And also, other than the external factors, it's also important to consider the internal degradation factors. For example, like I told you, the perovskite consists of these cations, anions, and which is having like anionic bonds, which can have like vacancies or interstitials. These ions can just move around the perovskite crystals. Sometimes this goes up and just react with this metal electrode, and it basically insulates it, and you don't have any more functioning solar cells. So you can see this is a cross-sectional image. You basically slice the device and you can see the metal electrode get eaten up by these ions. And what we can do is actually like the two strategies. One way the scientist is finding is also having to have a passivation layer between, so that it literally like blocks those ions to reach those silver layer. Or the other one is just to remove the silver and use an organic carbon, for example, which doesn't have anything to do with these ions, which is quite cool. And there is a work from Giulia Grancini in the year 2017, where she made a perovskite module using implementing both the strategies, where she used 2D material, like I was mentioning in the first slide, the advantage of 2D for stability, as well as she used carbon electrode, and she got like stability over 1 year, like around more than 10,000 hours. And also lately a lot of report, like articles also publishing if stability is more than 1 year, which is quite interesting, like with the studies where scientists working on different passivation, also different crystallization and grain growth of perovskites. And it's also important to mention, few months ago, the scientists in the field of perovskite, they made a consensus statement to assess the stability of perovskite following certain protocols, so that the scientists all around the world can follow a certain protocol or procedure to assess the stability. So now I like to talk about some market potential of perovskite. So the first one you can see is the Internet of Things. What it is actually the devices which are connecting to the internet. For example, like your smartwatch, which can get connected to the internet. And here, like I mentioned you, the biggest advantage of the perovskite, where you can tune the band gap of it. And Internet of Things, it can be used in indoor, like in the indoor lighting condition, or it can be taken outside. But I like to stress out a bit more in the indoor application, where you can tune the band gap, where the perovskite absorb more or harvest energy mostly on the indoor lighting conditions, like the one LED lights what we have in houses. So with the ability of tuning the band gap, we can have perovskite to be out from the other technologies. And if you see, International Data Corporation says the IoT spending over like $1 trillion in the year 2022. And also one interesting other market is going with BIPVs, where you can, like already explained you, taking the advantage of inkjet printing, where you can have different shapes, different patterns, and also we can fine tune the colors with changing the band gaps. So this is another market where we can go with the perovskite technology. And in global market, if you see, the size is like $36.74 billion in the year 2025. And the perovskite tandems, obviously, like Christina already mentioned about it, where you can have a lower bandgap material and a higher bandgap material, which are like both perovskites, Or we can also integrate onto other technologies. For example, silicon having like certain 1.1 band gap and trying the perovskite with a more higher band gap, and we can integrate onto that. Sorry, onto the lower band gap. And another interesting application would be also in the space. So lately there were also a lot of papers which studies shows that perovskite with the properties of like having a rapid self-healing mechanism. With this, it can actually withstand high energy gamma irradiations or like high energy electron or proton irradiation, which is quite interesting to see in the future for the human mankind, like when we have applications mostly in the space. So now I'd like to talk some of the companies which are trying to commercialize the perovskite technology. Well, first one is Saule Technologies, where they're working on inkjet printing of perovskite on flexible substrates. As you can, it's a Polish-based company in Wrocław. And the other one is Oxford PV, and they are based in UK, and they are working on silicon tandems, like with silicon and perovskite tandem, to harvest the larger spectrum of the sun. And also it's a startup company called Swiss Solar, where they're also working on high power to low weight ratio devices, and later in the modules. And this is a Chinese company called Microquanta, and they are working on perovskites on rigid glass substrate, and they claim to have efficiencies in the range of 18%, which is quite impressive. And these are other two companies, one 3D Solar in Israel, they're also planning to work on perovskite technology, and MET in Lithuania. So perovskite can be, like I already mentioned you, like outside photovoltaic. So perovskite can be also used in other applications, like the one which is used in light emitting diodes, where you basically apply a voltage and you can emit photons out from it. So this is one other property of perovskite, and the other one used as X-ray detectors, where you can have perovskite to absorb the X-ray photons, and you can see in this imaging technique. On the other one, or you can have like a water splitting property, you can act like a hydrogen fuel. You can split the water to hydrogen and oxygen and utilize this as a fuel. And or perovskite can be used also for amplifying this pump light to a higher intensities, which can be used as lasers. So in conclusion, perovskite, if you talk about efficiency, you can see this ramping up efficiency over the past 8 years, which is very impressive. And you can see over 25.2%, and in the case of large areas, it's in the range of 16%, which is very impressive. And I already talked about stability. Scientists are really working on high stable devices in the past few years, and you can see going more than 1 year of stability. And with the advantage of solution processability and also the low cost of the materials itself, we can see the future of perovskite to be in all over the market. And this is something great for the future. And thank you so much. Now I'll give to Luigi to talk about MAESTRO consortium.
Thank you very much, Vivek, and thank you all for arrived till this point. We are at really end of the webinar, so the following part will be the content of the part will be more easy to follow, so don't worry about all the math, all the chemistry and physics we did just in the last 4 talks. This part will be more, let's say, relaxing. We want to talk about our project, first of all. Why we are telling you this stuff about energy and perovskite and global warming? Mainly because we are funded by European Union, and we believe in the Sustainable Development Goals, and our project has some primary and secondary goals to follow. The primary ones are to reach and have an affordable and clean energy and talk about climate action. And the secondary goals relies on those points on industry, innovation and infrastructure, sustainable city and communities, to believe in the recycling and responsible consumption and production, and to believe in the partnership for the goals. But why we are telling you all this stuff, who we are actually. So we are called MAESTRO. MAESTRO stands for Making Perovskites Truly Exploitable. It's a project funded by the European Union that was started in 2017 and will finish late next year. It's an innovative training network from the Marie Curie Skłodowska action. And it's a consortium based on 17 companies and research institutes. And in this consortium, we have 15 early stage researchers. As you can see from the right-hand side, we, as also part of Europe, we believe in the multicultural dialogue and also to spread all these information all around our institutes. And you can see from, again, from the right-hand side that we have in our group physicists, chemists, material scientists, and process engineers. And we came from different parts of the world, even from America and Asia. And most of us are based in UK. The four of us are based in UK, whereas the majority of us is based in Europe, and we also have partners in Israel and 3G Solar and Bar-Ilan universities. We also have two external partners that belongs to the project that doesn't have any, we call ESR, that stands for early stage researchers, but they are part of the project that are Tiber Lab and NPL. Now let's go to what we are doing in our project, step by step, analyzing each and every early stage researchers. So Vivek told you about the perovskite, as the name MAESTRO stands for. It's making perovskite truly exploitable. We want to first study the theory behind this, and Thijs, working from University of Bath, is working on the multi-scale modeling to understand the perovskite by running big calculations. So he's the only guy that we have in our crew to help us to know better the theory behind all this technology. Then once we study the theory, we want to study the film, the real film. And we have four guys here that are working on film and device making process. And for instance, we have Lefteris from the center in Demokritos in Athens that works mainly on lead-free perovskite. Renee is working on toxic lead trapping using some encapsulant in 3G Solar in Israel. Nadia is working on the chemical synthesis on dopant-free all transpose material, as Christina told you about these selective contacts that we need in the perovskite technology. She's working in EPFL, Nadia. And then we have Philip that works in Oxford University, that is most working in finding the perfect structure for the most stable perovskite solar cell. So those guys are working on the synthesis and device making of this perovskite technology. So again, from the theory to the device and film making, we are going to also analyze and characterize this, and that's why we have these four members in the group. Augustin from UGI, University Jaume I in Spain, is working mainly on a specific tool that is called impedance spectroscopy that works mainly on the frequency domain of this technology. Pratibha, she's working in Bar-Ilan University in Israel, and she's studying the defect physics of light perovskites and also implication on doping. Then Emily from IIT in Milan, Italy, she's working on study the stability by applying a photophysical approach. And Christina, that she works for Oxford Photovoltaics, she's investigating the degradation of low gap perovskite for possible application in tandem solar cell. So those guys are mainly working on the film device analysis and spectroscopy. So again, from the theory to the device making people to the device analysis, once we did all this stuff, we want to upscale the process. That's why we have Vivek, Rahul, myself, and Reddy. So Vivek is working in Saul Technology in Poland, and is mainly work on flexible substrate, as well as Rahul, that he's working in Swansea University in UK. But the difference among them is that Vivek is using inkjet printing technology, like a normal, like the concept is the same as the printers that we have in our home. And also Rahul is instead is working on roll-to-roll manufacturing, so a big machine to allow the automatic process flow of the technology. Myself and Reddy are working in Rome, in Italy, and we are based mainly on glass substrate modules. I'm basically work on stability of modules, and also to optimize also the laser parameter to create a good series connection of the modules, whereas Reddy is mainly work on the low temperature process for making the perovskite at low temperature to reduce also the so-called life cycle analysis of the technology. So we are working on the scaling, and then last part of our group is mainly focused on possible tandem application of this technology using also with the help of silicon solar cells. So Vaidvila, she's working in Constance University, and she is working mainly on the bottom cell application in tandem devices, whereas Sijo is working in MGT in Vilnius, in Lithuania, is a company that sell photovoltaic panels, monocrystalline and polycrystalline silicon solar cell, and is working mainly on semi-transparent perovskite solar cell for perovskite tandem applications. So that's all of us, what we are doing specifically in our specific projects. So as you can see, there is a link that we can do all together. And as a project funded by the European Union, we also have some report to do to the European Commission, as you might be aware. And we can divide these big reports in working packages. The first one is regarding the materials, the second one is regards the device, and the third one is regarding the upscaling part of the process. Because we are a part of an innovative training network, we also get to learn some concept from get to know the perovskite technology, to characterize them, and also to visit some pilot line and companies. We were all around Europe, as you can see on the left hand side and our group picture. Just I want to mention that the last meeting we were supposed to go to Vilnius to visit the facility for MIT that works on the silicon technology, but because of the COVID-19 situation, we did this meeting online. But it was great. We learned a lot of stuff. Then so far we reached these publications, and many more are like in peer reviewed, so are really soon will be published. I just want to mention the last one that you can see by Vivek Babu, that he was just speaking before me. And he was improving the stability of inverted flexible perovskite solar cell using a carbon electrode. So as Vivek told you, just by replacing the metal with an organic material, we can also reach a stable perovskite, not only cell, but also module. With this, I just want to mention that there are more events coming soon, and maybe we will have also another Maestro webinar. You can check always our website there below, and also don't forget that there is a big energy week, that is European Sustainable Energy Week from 22 to 26 of June 2020, this month, and it will be totally virtual, so you can join by staying at home. And I also want to cite the PSEO conference, that is the main perovskite conference that will be take place next year, where all of us, all our ESRs, and myself and my colleagues will have an oral presentation during an entire morning. So if you want to check what we are doing, just come to Oxford next year in September. How to get involved? I will suggest you the first thing to do is to take the test, as Thijs showed you before, with the footprintcalculator.org. Then there are many other websites to check, like Cordis Europa.eu. If you want to work on this field, you can just type perovskite as a keyword and just check what pop up. I think there are many projects running on perovskite nowadays in Europe. And also I want to mention the European Perovskite Initiative, that is a white paper that all researchers on this field sign and wrote, just to get the public know about this beautiful technology. With this, I want to thank all our university and research center and companies that are working in this consortium, and also all the funding coming from the European Union that let this webinar get also for free for all of you. And thank you all for your kind attention. And now we have time for also some questions. Thank you again.
Thank you very much, everybody. We received quite a lot of questions from you, so we are very happy about it. Some of you also commented quite nicely on the chat, so thank you also for this. This is really encouraging that you liked our webinar. So I'm hosting the question sessions, and I will read the questions that we got, and then you will get your answers. But if we don't answer fully, maybe you can also, if it was your question, elaborate a little bit further with unmuting your microphone. Okay, so the first question we received is, how is perovskite reliable for large-scale applications? Would it really compete with silicon? Does somebody have the answer for this from our expert today? Yes, I thought so.
On this, so as I already shown in the processing techniques, where if you see perovskite, like the advantage of solution processability itself, and which can be used onto roll-to-roll processing, we can really increase the throughput and also the yield in the large-scale applications, and also as well as if you see the cost of the material itself. And would it really compete with? I think for now the state of perovskite, it's like still growing on with the technology itself. So I would say in the future, if we can see, as I also shown the different applications, we can really use the perovskite technology in a lot of applications where silicon cannot even come into place. Like for example, even like the indoor application, for example, where silicon can be mainly used for low band gap materials.
Vivek, I have another question for you. Maybe you can answer it. It's very specific, actually. So they are asking, how has Sauler technology managed the stability aspect of the R2R perovskite solar cells? Can you give input, or is it maybe too confidential?
I think it's a bit confidential, but I cannot like really give. So for example, like in the stability, in general, you can work on a lot. Like I was showing you the passivation layer, also working on different other electrodes, for example. And yes, for details, especially from Sauler, it's a bit confidential, sorry.
Okay, so then we received some other questions. I will continue. So one asked question was a little bit more broad, I would say. Are there gas layers that can't be built to prevent global warming? is there any research going on this topic? So maybe I'm just commenting. I guess it's not a good idea to increase other gas layers in our atmosphere, as the risk is very unknown. Of course, there are simulations that are trying to predict what could be beneficial or not, but maybe it's better just to focus on how to remove the greenhouse gases like CO2 from the atmosphere. And there was, for example, like a CO2 capture system just recently funded with $50 million US. So that might be maybe more beneficial. And also, you know, the Earth is protected by the ozone layer, and the ozone layer was seen over the last year that it's super decreasing. And so all the chemicals that actually decrease the ozone layer were banned. And the benefits for climate change with banning these chemicals was actually also that these were mainly greenhouse gases. So I think it's not necessary to put more gas in our atmosphere where we don't know the interaction with the sun. We don't want that it's getting even more severe than it is. We had another question. It is, so far degradation rate of perovskite devices is much faster than the one of silicon-based solar cells. In tandem devices consisted of silicon perovskite, this would cause a current mismatch. Is there any possible solution to solve reliability issue from different degradation rates of top and bottom cell?
Yeah, I can just mention something if you agree, guys.
Mm-hmm.
So
of course.
I think it's a good question actually. Thanks for asking. It's we need to think about the technology. So the perovskite technology jumped in 2012. So he has like just less than 10 years old. And silicon solar cell is a technology that is like more than 50 years into the research communities and also into the market. So I think we really need to focus now on the stability point of view. And once we already know that the stability is really good and we can make and construct really a good solar cell, then we can point out for tandem application. I can just mention that only a couple of years ago, companies on perovskite silicon for tandem application jump in, and they are quite close to the market, but they are not yet into the market. That means that the stability of perovskite is really improving a lot during the month, and there are some tricky treatment to do, such as Vivek told you in the talk, just to replacing some to choose the selective contacts, for instance, and also maybe to change the metal because it gets oxidized really soon. So the carbon replacement is a good way to step up the process, I would say.
And I have another question for Vivek. Many people are very interested in solar technology, I have the feeling. So one person is asking, can you please comment on the status of inkjet printed perovskite solar cells? How much is the design different from conventional designs, and how stable is the device?
Okay. So maybe the first comment, my colleague David Forgash already had a presentation during the HOB. We talk about this, like mentioning about the efficiency and stability. So we have efficiencies like on flexible substrate in the range of 18%. And if you talk about stability, we got like really amazing stability now really close to 10,000 hours. So we are like without any drop in efficiency. And also about inkjet printing, yes, it's quite amazing. Like for example, if you talk about inkjet printing, you can really control each and every drop which you want to deposit onto the surface. It's not like, this is something also different from other technologies like blade coating or slot die coating, for example, where you can really precisely say, okay, I want one drop onto a one particular position, you can do that. It's really a big magic of inkjet printing. So if you can think about, I need different shades of perovskite. For example, I need, at some areas I need thinner perovskite, some areas I need thicker perovskite. You can even do this with the property of inkjet printing. And if you talk about with this, yeah, stability, I have already mentioned it. So inkjet printing is like really amazing technology, honestly. And then it's also like to explore what can, for example, like I was mentioning about your BIPVs, which would be very applicable in this case.
Okay, thank you, Vivek. I hope this solves those questions. And another one for you, and then I think I will continue towards some other questions so other people can also answer, was, can you comment on the encapsulation methods you use in Saule?
I don't know if I can say what kind of encapsulation methods we use in Saule, but we work on flexible substrates in Saule, and so we obviously go for roll-to-roll encapsulation method. First and foremost important thing is what kind of adhesive we need to use. Like, as you guys all know, that perovskite is like can degrade onto polar solvents. So we need to be careful on the choose of adhesive material we want to use and what kind of technique. For example, in some cases, pressure could be also an impact when you. So like I told you, we go for roll to roll. If you have a pressure between the rollers, it can also affect on the acceleration of the degradation mechanism. And the other one is also like the temperature. Like it all depends on what kind of encapsulation technique you use. And yeah, in Saule, we use a roll-to-roll processing method.
Okay, thank you very much. So I think I have here a question maybe for Christina. Somebody asked why silicon wafer have honeycomb structure and why polysilicon have a rectangular or a square shape.
Yes, thank you for the question. So this is actually how can we easily distinguish the mono from polycrystalline silicon. So the shape of hexagonal or honeycomb shape of the monocrystalline silicon stems from the fact that you have one single crystal of silicon. So this shape is due to its orientation. Whereas in case of polycrystalline silicon, you have small crystals on your film. So that's why you can actually have whatever shape you want.
Okay, thank you for this. I hope it helped. Yeah, so there's another question concerning the stability. I also saw in the chat that many people are interested in the whole stability issue. So maybe somebody can comment how the stability of perovskite solar cell is in the module level.
Yeah, if you want, I can comment something, and I also, if you allow me to do, I can share my screen.
Yes, of course. Please, Luigi, go ahead.
Yeah, thank you. So actually, this is a really good question because we are in the papers, in the scientific papers, they always talk about stability of solar cells, but there are really only few papers on stability of modules. And what I find out is that there is only one paper in Journal of Physics of Energy by Julia Gallagher. She is working in TNO, is a big, let's say, research center in Eindhoven and in Netherlands. And this is the only paper I found about the stability of perovskite PV modules. And what it says is that there are many degradation effects occurring at the interconnection between modules, as you can see here. As you might know, or you might not know, the difference between solar cells and modules is that a module is just a series interconnected of cell. So there are only like cells interconnected in series, and we use these names like P1, P2, and P3 scribe just to let the current flow along each cell. And the fact that, for instance, here for the P2 scribing, there is a free space in which the metal can jump in. What it tells you, it tells that the metal, like the most common one is gold, is touching the perovskite layer, and this is cause the main degradation for the modules. So what is a good strategy that Gallagher said is to use a diffusion barrier layer that is a kind of covering this gap between the P2 and the metal connection. So there are strategies to improve the stability, but we also need to improve stability on modules. That is another issue. So that's the beauty of the perovskite, and it's part of our research.
Okay, thank you very much, Luigi. We have another interesting question for Thijs. And it's asked, what is the average LCOE of perovskites? You prepared a slide on this, I think.
Yeah, let me just quickly show it if I can.
I'm showing it already, I think.
Ah, sorry, yes. Yeah, it's a really good question, I think, because in principle, the way for us to get into the market, of course, goes with how expensive we can make these modules or perovskites with. And of course, we're still, as has been said previously also in the Q&A, developing this technology. So, and there are some companies / startups out there, so it does seem to be really competitive. But to put a number on this is still, we still need some assumptions. And one is that we assume in this case, for these two papers, I've shown the references below, that we need to get lifetimes much higher than what we have today. But if we do so, we get costs that are competitive or even below fossil fuel prices, as mentioned before. And even more strikingly, I think, is maybe what the second paper shows in the bottom two figures, is that the price of perovskite by itself, so either a perovskite single junction module or a perovskite tandem, could have costs quite a bit below silicon modules. So there is for sure a potential, like a market potential there, but yeah, we still have work to do, put it that way.
Okay, thank you very much, Thijs. So I would say you have really many questions for us, but I would say we do like 3 more, and then we're ending this webinar, as you're already like saying quite a long time with us, which we're very thankful for. So for Christina, there's another question, and they're asking, why are we unable to increase the efficiency of inorganic perovskite solar cells?
So if you consider the lead-based cesium-lead triodide, theoretically you can have high efficiencies if you extract the calculated current from absorption coefficient. However, cesium-lead triodide is quite unstable in room temperature, so due to this instability, its performance is quite poor. And also, if we go for lead-free perovskites like F18 triodide, then tin have other issues regarding stability, so that's why again the efficiencies are quite low.
Okay, thank you, Christina. Now we have also an interesting question, which is about the toxicity. So what is the lead toxicity issue? What is the potential for lead-free perovskite? And are there prospects on the stability of peroxide? I think the third one we already answered a bit, but maybe Christina and Vivek, you could discuss the first 2 questions.
Yeah, may I?
Yes, please.
Regarding lead toxicity, it's quite a controversial topic, so a lot of studies are still in progress and investigating the toxicity of lead and how dangerous could be, and also the option of recycling that I think someone has already.
Yeah.
And regarding lead-free perovskites, you can substitute lead with other materials. The most promising now is tin, but again, you can combine also double perovskites like bismuth and silver. But their efficiencies are quite low and their band gap is not ideal, especially for the double perovskites. Regarding tin, many improvements have been made, but still there's a long way until the impressive 25% of lead-based.
Thanks, Christian. Maybe I'd like to add one more comment. Not recently, like a few months ago, there was also a Nature paper where they used a polymer layer to trap those leads. So basically, they encapsulate this module and they basically have this polymer layer in between, and they made a lot of damage onto the module and they dip it into the water. And then it seems that this polymer material can absorb this light and not letting it outside. So this is also something I like to address, where we can also trap it inside, not letting it outside. That's the case where you don't need to deal with the toxicity issues.
Okay, so our last question. It's for Christina. What is the future of perovskite-based tandem solar cells?
Yeah. So as you can see, especially the company that I'm based for is active on perovskite tandem solar cells on silicon. So there's a lot of work being done, and many companies try to industrialize this technology, even with installation of large area manufacturing equipment and facilities. So yeah, we don't know yet. Again, perovskites have some issues that need to be solved anyways. So the future is bright, and we will see. Regarding all perovskite tandem solar cells, again, you can combine two different perovskite materials with different band gaps, and they have really remarkable efficiencies by far. But again, we have this stability issue that we need to optimize the material and solve this issue. But let's see.
Okay, thank you very much, Christina. I would like to give the word now to our project coordinator, Alison Walker from the University of Bath. She is present today during our webinar, of course, and she would like to give some final words.
Hello, can you all hear me?
Yes, it's working fine.
Okay, well, really all I want to do is to thank everyone involved with creating this webinar. We're starting with Annie, who set up the technology and introduced the webinar, my colleague. I'd like to thank Nadia, Thijs, Christina, Vivek, and Luigi for just giving an amazingly effective webinar. I know you guys have taken some effort to do it, and I can say that it's worked in spades. It's worked fantastically well. So I would also like to thank the European Commission, and we've had a lot of support from them, in particular from our project officer. So I think, as has already been said, the future is bright, not just with the perovskites, but with these young people who are busy to create this new technology. So 3 cheers for you all. So I'll finish on this. Perhaps, well, finally, of course, to the audience and the very enthusiastic number of questions we've had, we really appreciate your participating in the webinar. Okay, so I think I'd like to finish on that note.
Thank you very much, Alison, and thank you very much, everybody, for joining today. Without your participation, this webinar would have been not so successful. So thank you very much for listening to our talk. And I hope you had a good day, and I hope you could really learn also some new interesting things. Okay, you can disconnect if you like. Goodbye. Thank you so much.
Thank you, everybody.
Bye, guys. Thank you.